Okay, so the second half of this unit deals with some more concrete and visual applications of integrals, right? So we spent a lot of time being like, this will prepare you for more math things. And now we're kind of taking a break from that and being like, this is how we actually use calculus in the real world, okay? So we're going to start with today, we're going to focus on work, the idea of how much work does it take to do something. And again, if we have time, we'll move on to the centers of mass, which is also kind of a cool application. I will start this by saying I am not, though I was an engineer major in undergrad, I am not an engineer by trade. So it has been many, many years since I have thought about like all the different kinds of applications of these. So there may be some questions about applications that I just don't know right now, but I'll do my best to answer those. And with that being said, we will get started. Okay, so we have 6.5 in the textbook, which is a section called work, right? So depending on what courses you have taken so far or what your academic background is or what your work background is, your professional background, you may or may not know that this idea of work is nothing more than force times distance, okay? And this is a formula that maybe you've seen in physics or whatever, and you see this formula often as W equals F times D, or work equals force times distance. Now, you might have even seen this in like high school if you took physics in high school, but this formula is actually only true for a very specific case. And this is a specific case where the force is applied is constant in nature, okay? So you're applying the same amount of force for the entire distance, you're not changing it, or there are not external factors that are changing the force that you apply to whatever you're applying it to. And so a diagram for this, if we think about this, might look something like this. All right, and I'm not going to draw the negative side just because we typically think about the distance as being like a starting distance and a stopping distance, sort of being on the positive side. But this force, if I think about it on a graph, okay, is really, if it's constant, then it looks like this. All right, so this is our force. And so this formula really allows us to say, you're going to start at a certain point and you're going to finish applying the force. You're going to stop applying the force at a certain distance. And so this part right here represents the distance over which you apply that force. And so really, force times distance is a fancy area of a rectangle formula. Okay, this is nothing more than the area of a rectangle. Now, it's a really great way to introduce this idea of work and force and distance, especially to folks who are maybe like 14, 15 years old, right? We want to get the idea that if you apply force over a given distance, you'll get the amount of work that it takes. So this purple squiggle here represents the work, okay? But now that we're more grown up, we're going to take a look at what happens when we have non-constant forces, okay? And so this, let's keep the colors the same. This f of x represents a non-constant force, okay? And believe it or not, that dx So that distance right here, this dx, and our bounds tell us that we're going to start and stop at a certain place. And the dx tells us we're going to take an infinite number of slices so that we end up with the most accurate area. So we're not approximating the area, we're getting an exact area for a sort of wavy looking curve. All right, so maybe the distance is better stated as this A to B tells us where we start and where we stop. And then our resulting answer will give us the work that it takes when we apply that non-constant force over a given distance. And so if we think about a diagram, we might end up with something that is a little bit more squiggly in nature, right? And this would be our force. And we would still have a starting point and a stopping point, and then the area here still represents the work, okay? But that area we can see from the graph, like the one on the left is a rectangle, we definitely know how to do that, but the one on the right requires an integral if we want to get an accurate answer, okay? So that's sort of what we're going to be focusing on for this section. Now we're going to take a look at sort of two different scenarios, okay? There's a lot of other work applications. These are going to be the two that we focus on in this course, right? So we're going to focus on springs. Some of you may have heard about something called Hooke's law. And Hooke's law states that the force required to stretch a spring x units beyond its natural length is simply a linear situation. F of x equals kx, where k is a constant called the spring constant. Now, what we mean by that is if we think about these two diagrams above, we had like the very simple diagram on the left and a little bit more complicated diagram on the right. But if we're wanting to put a diagram for Hooke's law, okay, what we're really looking at is somewhere in between the diagram on the left and the diagram on the right. So it's not as easy as a rectangle, but it's not as complicated as a curve. And what we have here is we have some sort of linear function, okay? And this function has a slope of k, and we have x as our variable that we're taking a look at. And then what we're going to be trying to do is finding the amount of work it takes to either stretch or compress springs over a given distance. So we could start somewhere, we could finish somewhere, and that area is going to represent the amount of work it takes to stretch or compress the spring. We could use area formulas here, like the shape that I shaded in this little diagram, that's a trapezoid. We know how to find the area of the trapezoid. But we could also find this using integrals, okay? So we're gonna practice using our integrals so that we can think about how this might apply to more complex systems in the future. All right, so if you get all the way to differential equations, you're going to come back and see a lot of the applications that we're doing right now again, and we'll just be doing them with more complicated functions at that point. All right, so if we think about springs, okay, so every spring has what we call a natural length, meaning that's just how it is when it's just sitting there. Okay, nobody's pulling on it, nobody's smushing it, it's just sitting there. We call that its natural length, okay? And whatever the natural length is, we tend to say that that natural length is gonna be called 0, because that's like our baseline, okay? Anything we do beyond that is the stretching that we're doing, or similarly, we could also compress it by a certain amount, and that differential is what we consider to be our A and our B. So we're looking for the how much did it change, not necessarily where it started and where it stopped. Okay, so look for how much change happens, right? You can almost think about this like, sometimes some folks, let's say, are very talented academically, and they've always kind of been that way. And so to them, an A is an A, but maybe that's sort of their quote unquote natural length. But then there are some folks out there who, for a variety of reasons, might need to put a little bit more work into achieving that A or that B, right? So that difference between the natural length and the stretched length, that amount of growth is something that we should recognize, right? So when we're looking at the natural length to the stretched length, we're really seeing like how much change happens, not just like where did it start initially and where did it stop, but like what's the difference, because the work happens in that difference. Okay, so let's take a look at example number 1. So a spring has a natural length of 20 centimeters. A 40 Newton force is required to stretch and hold the spring to a length of 30 centimeters. How much work is done in stretching the spring from 35 centimeters to 38 centimeters? So in this first question, we're going to have to focus on a few things. We're going to focus on the formula and the setup, but we're also going to talk a little bit about the units, okay? So the newtons right here, the units for that are kilograms times meters per second squared, okay? The part that sticks out to me is that I'm dealing with meters here, but all of the length that I'm given is in centimeters. So before I do anything else, I'm going to convert all my length to meters so that it matches the newtons. So this 20 centimeters is going to be 0.2 meters. Okay. This 30 centimeters is going to be 0.3 meters. This is going to be 0.35 meters, and this is going to be 0.38 meters. Okay. Now, in a lot of these problems, it's a little bit less important when you're working with like feet and pounds. But with newtons, you do want to make sure everything is with meters and kilograms and seconds. Okay. So now that we've changed all of our lengths, let's go ahead and set up our equation. So we've got work equals the integral from A to B of my force. And did they use a capital F? Some people use a capital F, some people use a lowercase f. I think I tend to use the capital one because force is usually with a capital and the lowercase f in math is usually like a function. But your physics professor might say differently, so just be aware of that. But in this case, if I think about what I have my A and my B, and because I'm working with springs, I can go ahead and use Hooke's law. So instead of F of X, or the force, I can replace it with a spring constant times X. Okay. Now every spring has a different spring constant. And so our first step is actually going to be to find our spring constant, because once we find our spring constant, what we really have is the slope of our line. And so that's going to help us integrate and go from there. Okay. So our first step is going to be to find your spring constant for this spring. So if you're working on a different problem, you cannot use the same spring constant. For every spring situation, you have to find the spring constant. And so we're going to just plug in the numbers that we have. So we know that work equals, we know that our force equals our spring constant times x, okay? So our force that was applied is 40 newtons, because that's what it said in the problem. Our K is what we're trying to find. But how far did this spring get stretched in order, or after we applied 40 newtons?
0.1 meters.
What was that?
0.1 meters.
0.1 meters. Yeah, I thought I only caught the second part. So I was like, I'm pretty sure he said a point in there. Okay.
I think the internet's going out.
So we're gonna, in order to find the 0.1, we could think about it like the ending length minus the starting length, and that's how we get that 0.1, okay? And then to find K, we just divide 40 by the 0.1, we'll get 400 as our spring constant. Now that we have the spring constant, we can set up our integral. So our integral is really gonna be a 400x dx, okay? But they wanna find the work done in stretching it from 35 centimeters to 38 centimeters. So in our bounds, here's what we're not going to do, okay? We're not gonna put 0.35 down here and 0.38. So I put that in red because I don't want you to do that, okay? Instead, we have to think 0.35 is how much bigger than the natural length. And 0.38 is how much bigger than the natural length. Okay, so it's all relative to the natural length. So instead of putting 0.35, we're going to modify that. Okay, and we're going to put 0.35 minus 0.2. Now, I'm writing that instead of 0.15 because I know you guys know that's 0.15, but when you come back to do your quiz or you're studying, like, I want you to remember where those numbers came from. And so same thing with this 0.38. We don't want 0.38. We want 0.38 minus 0.2. We want how far did it stretch from the natural length. And so that gives us 400, the integral of 0.15 to 0.18 of x dx, okay? So a lot of the complexity of this problem is in the setup, but this integral is one of the easiest ones that we've seen in a really long time, right? So I hope it's a little bit of a breath of fresh air, because we're not trying to find some weird trig substitutions and this and that. All we need is the power rule. And so when we integrate, we end up with 200x squared. We're going to plug in 0.18. We're going to plug in 0.15, and we're going to subtract the 2. And we should end up with about 1.98 joules. Okay. So that's a very basic spring problem, but for most of these, you are gonna need to find your spring constant before you can do anything else, okay? So sometimes, especially for those of you who really like to do that pre-thinking so you don't have to do that work later, you can consider finding the spring constant as that pre-thinking so that you already have your equation when you go into your integral, all right? All right. So let's take a look at a similar problem, but we're going to be working with some different units. And so let's think about how the units impact the units of our answer and whether or not, like what stays the same and what's different, okay? So example 2 says a force of 9 pounds is required to stretch a spring from its natural length of 6 inches to a length of 8 inches. So right off the bat, they've given you all the information you need to find that spring constant. Okay. Now part A says find the work done in stretching the spring from its natural length to a length of 10 inches. And then part B says find the work done in stretching the spring from a length of 7 inches to a length of 9 inches. Okay. So these two parts, what I'm trying to highlight here is that the bounds are going to be different, but the function is actually going to be the same. So the thing that we're integrating is the same. And if we are looking for the answers, only thing we need to change differently is we need to make sure that our bounds reflect what we're talking about. Kind of like when we did the polar, how like it was different if we did negative pi over 3 to pi over 3 versus pi over 3 to 5 pi over 3. The bounds here are really what's going to help us find the different answer. So let's set up our integrals. But before we do that, let's find our spring constant because we're going to need that for parts A and B. Okay, so find K. All right, so I know that the force was 9 pounds, and that is the spring constant times it's stretched from, or stretched to 8 from a natural length of 6. Okay. And so we find our spring constant here to be 9 halves. We can use this for both part A and for part B. So to find our work in part A, all right, we know we're going to have the integral of 9 halves x dx. What are our bounds going to be?
0 to 4.
How'd you get that? Because I don't see 0 to 4 anywhere in the question.
Your lower bounds would be whatever length you're starting at minus your natural length, and then your upper bounds would be your ending length minus your natural length.
Yeah, so because it's the natural length, and we subtract our natural length, we're starting from the beginning, right? We're starting from 0. But if we're stretching it to 10, we're not stretching it a total of 10 inches. We're stretching it from 6 inches to a length of 10 inches. And so we're going to do 10 minus 6 to get the top bound. Okay. And so this will give us 9 halves the integral from 0 to 4, as James said originally, of x dx. Okay. Let's integrate. We get 9 over 4 x squared. We're going to plug in 4. We're going to plug in 0. And that is going to give us 9/4 times 4 times 4. And if I plug in 0, it's going to go to 0. But again, this is a great chance to show you again, like I'm not going to multiply 9 times 4 times 4 and then divide it by 4. I'm just going to reduce here. So save myself a little bit of, multiplying out some big numbers, because really it's just 9 times 4, which is going to give me 36. And then our units here, so when we're talking about feet and pounds and inches, we don't need to worry so much about the units like we did with example number 1, okay? So these units are just going to be inch pounds, 36 inch pounds. So that's how much work is done to stretch the spring from its natural length to a length of 10 inches, right? Now, before we do part B, do we think that that is going to take more work or less work?
It depends on the K.
Well, we have our K
I think it'll be less work.
though. Okay. Why do you think it'll be less work?
It travels less distance.
Yeah, it only goes from 7 to 9, okay? Versus like the first one was 3 whole inches in terms of the change, okay? So for part B, we don't need to find K again because it's the same spring as part A, so we know our equation. The only thing that's going to change, and I'll move that 9/2 out to the front, is our bound. So what's our bottom bound in this case?
1.
1, 2, 3.
It's going to be 7 minus 6, or 1, right? Because 7 is where I'm sort of starting to count the work from, but that is not, I haven't stretched it 7 inches. I've only stretched it 1 inch from the natural length of the spring. Okay? That means my top bound is going to be 9 minus 6, or 3 inches. And then I have x. Whoa. Then I have x dx. All right. This integral is going to be the same, 9 over 4x squared, but I'm going to plug in 3 and I'm going to plug in 1. So that gives me 9/4 times 3 squared is 9 minus 1. So 9/4 times 8. And if I reduce here, I get 2. And so, Mariah, you are correct. This is less work to stretch a spring from 7 inches to 9 inches than it is to stretch it from 6 inches to 10 inches.
What if you're compressing the string? Work.
You can still use the same formula. So it's just going to have like different bounds. Okay, so stretching and compressing is still that same idea. They still both obey Hooke's law. All right, so this is the first application that we're focusing on. So springs, all right? So again, goes back to this idea that we can follow a linear sort of relationship, that the spring constant, in fact, gives us the slope of our function that we're integrating. We could always confirm our answers using a trapezoid formula or maybe a triangle, depending on what the shape looks like. But at the end of the day, we're really just finding our spring constant, plugging it into the formula, making sure we have the correct bound, and then integrating. All right. So the second scenario that we're going to look at is lifting objects, okay? So in particular, we're going to take a look at one scenario where we have a tank full of water, and we're trying to pump the water over the top of the tank. So we're trying to remove the water from the tank, okay? The other scenario we're going to look at, and we'll just kind of scroll down and take a look at this, is we're looking at a situation where we have a cable and there is a bucket attached to the end, and we want to figure out how much work it's going to take to pull that bucket up to whatever height we want to, okay? So those are our two scenarios that we're going to take a look at. So let's start with example 3. So it says a right circular conical tank of altitude 20 feet and radius of base 5 feet has its vertex at ground level, and the axis is vertical. So if the tank is full of water, find the work done in pumping the water over the top of the tank. And so I've included a diagram here. I think it's a very messy diagram the way it is right now. There's a lot of information. And so I want us to kind of take a few steps back and think about how this diagram came to be. okay? So we're gonna almost start from where we would probably start with the diagram and figure out how they got to this diagram, okay? So let's try this out. So if I'm reading this question and it says that there's a right circular conical tank, the first thing I do is I draw a cone with the vertex at the bottom. Okay, so I just get that from reading the first part of the equation. And so I have a cone and the vertex is at the bottom. So it looks very much like an ice cream cone. And I label it with some of the information I'm given. Like the height of this cone is 20 feet. And you could use like one of those for feet if you want. And the radius, I should have left myself a little bit more room. The radius here is 5 feet. Okay. So that diagram, I think we're all capable of drawing, right? We can label the height, we can label the radius, we know what a cone looks like. That part's not hard. So how in the world did they get from that diagram to the one on the left? Okay. So one of the things that we'll see over the next few units is that coordinate systems, whatever we choose for that coordinate system, we can choose what's going to make the most sense for any given problem. Some of us might choose it one way, some of us might choose a different axis, but at the end of the day, we should still be able to get to the same answer, okay? So when I'm thinking about an axis, like a coordinate axis that would be useful, I think about having just like an XY, okay? And I'm gonna go ahead and put the vertex of the cone at the origin, okay? So I've got my cone and it comes down to the origin. Whoa. Right, so all I've done is take the picture I first drew and just put it on some coordinate axes, because that allows me to kind of count a little bit better so that I can set up some equations, okay? So before I called this part the height, but on an XY coordinate, maybe we know that height is the equivalent of the Y value, right? Because we're going up the cone, and so that is the same as the Y axis in our diagram. Now, if we think about the radius, okay, so the radius, we could then think about as an X value. What does that make? Like if I pick a random point on this cone, okay, so let's say I pick that point right there. I could represent this as R comma H, right? Whatever the radius is at that part of the cone and whatever the height is at that part of the cone, that's going to be the coordinate of that point. Okay. Now, you might not want to use R and H. You might want to get it back to X and Y because that's what we're going to use when we integrate, okay? So let's do a few things here. What's the coordinate of that point right there?
5 and 20.
5 comma 20. How did you get that?
Just by looking at the diagram.
Yeah, because the radius is 5 and the height is 20, so 5 comma 20, right? Now, let's generalize this. So 5 comma 20 is that specific point. But every time I have an X value, I'm going to multiply by what to get the Y value?
4.
4, okay? And so we can even think about like from here, okay? We know this is the x value. And then I think about the ratios always being the same in a cone. So how do I get from 5 to 20? Well, I multiply by 4. In other words, I take the x value and I multiply it by 4. Okay? So the radius is x, but the height, instead of calling it y, we can call it 4x. What if I wanted to define this in terms of y? Like y is the height. What would I call x then?
Y over 4.
Yes, how did you get that?
You just divide that in order to get back.
Yeah, right? So we know to go from 5 to 20, we multiply by 4, but how do we go from 20 to 5? Well, we divide by 4. So that's why we have a y divided by 4, okay? So both of these are ways that we could name the specific point that we're looking at, x comma 4x or y over 4 comma y, right? All right, so let's do one more thing here, okay? So now I'm gonna draw this diagram and I'm going to strip away a little bit more so that we can kind of see how they get to that diagram at the end, all right? So, okay. So all I'm gonna do is draw the right half of the cone, but in 2-dimension. So that's going to give me something like this, with this point at the end being 5 comma 20. And then I know that I'm going to stop here, and that's at y equals 20, okay? Any questions so far? Or maybe too many questions.
So far, so good.
Okay. All right. So let's go back to this idea of work. Okay. So work is distance times force. We know that from earlier. We know that from the spring example. We know that from the general case. And so we could also say that we have this distance, okay? But instead of saying times force, we're going to say that force is the same as the weight, meaning the weight of the water. So force and weight are equivalent. But we can expand this more to say that we have distance times, instead of weight, we can find that it is the density times the volume, okay? So remember, we are trying to use integrals here because we don't want to sit and find the volume of every single little slice. Like, that's a lot, okay? We want to use this idea of integration where we can take an infinite number of tiny slices and add them all up together, and boom, we've got the exact force or the weight, all right? So we're going to make one more change here. This volume, okay? Now let's go back to our diagram, the original one that we started with. So they draw the cone. All of that looks very similar to what we have, but the one thing they have that we don't have is this little guy right here, okay? So you see how they have like a little cylinder that cylinder represents a slice of the water, in this case, the water that we're pumping out. Or if the tank was full of oil, that slice would represent a slice of the oil, okay? Now, we would not want to slice that thick. We would want to find very thin slices so that it's almost like it's two-dimensional so that we can find the volume. So here's where this last part happens, okay? So the volume, the shape that I highlighted there is a cylinder. So the volume of a cylinder, anybody know that equation? Yeah, pi r squared h. So we've got pi r squared and the height of the cylinder, okay? So instead of height, I'm gonna write thickness because what I'm referring to is how thick this little yellow slice is, okay? So instead of height, I'm gonna write thickness. Now, here's the part where when we bring it back to the calculus, it makes it a little bit easier. So we have pi r squared, because it's a circle. But if we want our slices to be super thin and then we're going to add them up over a certain distance, then the thickness is no more than dx or dy. Meaning we don't have to come up with an expression for it. It gets taken care of in our integral, all right? Now, in this diagram, in all of our diagrams, if we slice these little cylinders, are we stacking the cylinders up the x-axis or the y-axis?
Y-axis.
Yeah, we're stacking this up the y-axis. So check this out. If I'm stacking up the y-axis, that means I need dy. If I'm stacking up the y-axis and I'm using dy, that means the equations inside of my integral had better have y's. Okay. There's nothing wrong with the x and the 4x if I were stacking this along the x-axis, like a sideways tank. But in this case, we're trying to pump water up and out, which is in the y direction, okay? Okay, so all of this is to give you just a little bit of background, a lot of bit of background, more than you ever wanted to know about where this formula comes from, okay? So when you look in a textbook, usually this is what they tell you. They tell you the work equals the integral from a to b of your force function dx, right? That's sort of our general, we just happen to use x's. But we know in this case, we're going to change our perspective to y's so that we can represent things being pumped out and out the top. So really, we're going to say the integral from a to b of distance. That's going to be one thing you need to find in order to put your integral together, times force, which is really density times volume. So distance times density times volume. And we're going to seal this off with a dy because we know that we're stacking the cylinders up the y-axis. Now, our job is to fill in all the different numbers, okay? So I'm going to say that our distance is how far the water needs to travel, okay? And so the distance that the water needs to travel, it needs to go up to this 20, right? So if I said distance is the y value, that would just be telling me how much is left in the tank. That's what a y value would represent. But that's not what I want. I don't care about how much is left in there. I care about how far it is from the top, because it's going to take more work to get the bottom water out than it is to get the top water out. The top water is closer to the top. So to find the distance, we can't just put y. We have to say 20 minus y, because that tells us how far the water is traveling in order to leave the tank. So our distance is 20 minus y. Okay. All right, next up in our formula is density. So density depends on whatever substance you have inside of your tank. In this case, we have water. And so the density of water, when we're using feet and pounds, that density is 62, 62.5. Okay, that's the constant that we'll use for density of water. And so all we've done is replace density with 62.5. Okay. All right, last up is our volume. So our volume, we can use our pi r squared. Okay. So I'm going to put a pi, and instead of r, I could put x. What else can I put instead of r?
Y divided by 4.
Y divided by 4. Okay. Now, if I had a dx at the end, I would 100% put an x here. But since I have a dy at the end, I want to call it by its other name, y over 4, and square that. That will give me pi r squared. And then I have my dy. Okay. Let's just finish this. The volume is the pi r squared. All right. Now, some of the videos out there and some of the example problems, they put the 62.5 and the pi together. And I get that because they're both constants, right? So when we go through our integral, we're going to factor out that 62.5 pi. But they don't go together in the sense that, like, together they make up one component of your equation. The 62.5 comes from the density and the pi comes from the volume, okay? All right. Last thing is the bounds. We start at the top. The top water only travels 0. It doesn't go anywhere. Or I mean, it does, but it's already at the top. The bottom water is how far away from the top.
$20?
Yeah, the bottom water is 20 feet away from the top. So that's where our bounds come from. We have 0 to 20. That's the 20 is the maximum distance that the water is going to travel, and 0 is the minimum distance the water is going to travel. Okay. All right. So in terms of integrating, it's actually not that bad once we pull out all the constant. I'm going to take out the 62.5. I'm going to take out the pi. And I'm going to take out not a 4, but a 16, because it's 4 squared. That means in the front, I'll have 62.5 pi over 16. The integral from 0 to 20 of what's left, 20 minus y times y squared. Okay, not so bad to take an integral of. right? Just the power rule, that's it. So when we integrate, we'll get 20y cubed over 3 minus y to the 4th over 4. We're going to plug in 20. We're going to plug in 0. Okay. Now, some of you on either the tests or the quizzes have kind of just like left it as whatever number it is plugged in. So for example, I saw a few answers that looked like something like that, okay? That's fine, honestly. From here, I can tell whether you set it up right or set it up wrong, right? I think for some of the questions, they will be calculator okay. If you wanted to turn this into a decimal, then you would just type that all in. And I believe what you get is, and because we're working in feet, we have foot-pounds. Okay, so here's the whole question on one page of the amount of work it takes to pump water out of a cone, all right, or a tank. Now there are variations on this. So your R and your H, like that diagram, and finding out that the relationship is x comma 4x, like that might be a little different for different shaped tanks, but the idea there is still very similar, okay? We're not going to be looking at really wonky looking tanks. It'll usually be either a cone or a cylinder. Those are sort of the two classic cases. But hopefully with the color coding here, we'll be able to distinguish like what stays the same and what changes between the problems, okay? I think this is a good place to stop for today. I don't have any real desire to cram in example number 4 in 5 minutes and hope that it sticks with you. So let's save that one for tomorrow. We'll finish 6.5 tomorrow, and then we'll work through 6.7 and 6.8 and kind of see how far we get, okay? So I'm gonna stop sharing this. I'm gonna stop